So this will be our third lesson with exponents, and we're going to begin looking at exponent laws today. We're going to look at two different exponent laws. The first question, all I want us to do is write this out in expanded version with no brackets. So if we did that, this first yellow piece, we've got 5 multiplied by 5 multiplied by 5 multiplied by 5. So that's from the yellow piece there. From this blue piece, the second piece there, we have multiplied by 5 multiplied by 5. There's two of them there. So this would be our expanded form, or expanded notation. And if I wanted you to write it in index notation, notice that we have 6 5's multiplied by themselves, and therefore I could write it as 5 to the power of 6. Alright, so nothing really new there. Alright, let's look at number 2. So again, first thing, let's write it in expanded notation, and then we'll write it in index notation. So from this blue piece here, we have 4 multiplied by 4. And let's make the second piece the 4 to the power of 3, the green piece, and then we have 4 multiplied by 4 multiplied by 4, 3 times, because our exponent is 3. So of course this is expanded. And if I wanted us to write it in index notation, you would say, okay, well, there's 5 4's being multiplied by themselves, so it would be 4 to the power of 5, and this is index notation. So there's something that I want you to notice here. So I'm just going to over here, do a little aside. So notice that 4 to the power of 2 multiplied by 4 to the power of 3. Notice that if I was to add these two exponents, so 2 plus 3 is 5, I actually get 5, which is our answer in index notation. So notice that if I do 4 to the power of 2 plus 3, we get 4 to the power of 5. And in both cases, we get the same answer. We're going to generalize on that in a few minutes. Alright, let's look at number 3. So we have these written, it's already written in expanded version, but let's simplify. Okay, so our first step, let's just simplify. Okay, so we've got this 7 and this 7, and if we divide them, they become 1. And there's another one there, we can simplify this 7 and this 7, and they become a 1. So what I end up with on the top is 7 multiplied by 7 multiplied by 7 over 1. We don't really need to write this piece. Anything divided by 1 is itself. So in fact, I'm just going to erase this, and what I'm left with is 7 multiplied by 7 multiplied by 7. If I ask you to write this in notation, or index notation, we would have 7 to the power of 3. And if, I want you to notice this too, so that was pretty easy. Let's take it to the next step. Let's start with it where our numerator and denominator are in index notation, and let's see if we can generalize on that as well. So my first step, again, let's write this in expanded version. So we have 3 multiplied by 3 multiplied by 3. So that's coming from here. And my denominator, we have 3 multiplied by 3. Now let's simplify. Okay, so I've expanded it. Next I'm going to simplify, and notice that there's a 3 and a 3 there. 3 divided by 3 is 1. And there's another one that we can simplify here. 3 divided by 3 is 1. And all that I'm left with is 3. Now, of course, in index notation, we could write it as 3 to the power of 1. However, in general in math, we don't need to write this exponent 1. So in fact, our solution that we would want to keep with is just 3. If the question did ask you for index notation, then sure, 3 to the power of 1 is acceptable. Now what I want you to notice here is we've got, so our question was 3 to the power of 3 divided by 3 squared, and our answer we know is 3 to the power of 1, or just 3. Well, what I want you to notice is that if I take this exponent and I subtract this exponent, notice that I get 1. So what did I just say? Well, 3 to the power of 3 minus 2 is equal to 3 to the power of 1, which is also just equal to 3. And notice that our solution is what we wanted. Alright, so let's look at those rules. So first we have the product rule. Okay, the product rule, all it's saying, it was the first two examples that we were looking at, is if you have your base a, now the bases must be the same, okay, and you have two exponents, m and n, then if I want the shortcut for this, all I do is I take the base and I add together m and n, just as we saw before. So just a little example here, say I have 5 to the power of 100 multiplied by 5 to the power of 150. Okay, so I don't want to write this in expanded version. It's going to take me way too much time. It's a waste of my time. It's a lot of paper involved. Well, my shortcut's saying, okay, these bases are the same, and therefore all I have to do is add the exponents. So my solution would be 5 to the power of 100 plus 150, and of course I want to simplify this. This is 5 to the power of 250. And that's really why we like this rule, is because when we have exponents that are really big, like 100 or 150, or maybe even a million, very easily we can shortcut it and find out the simplified index version. So my question is, can you use the product rule for the following? Why or why not? So I have 5, and the exponent is 2, so 5 to the power of 2, and then I have 6 to the power of 2. Now this is a big no, okay? We cannot use the product rule because the bases are not the same, or not equal, okay? I think we all can agree that 5 does not equal 6. This rule can only exist, or you can only use it, if you have the bases the same. And that's what they were referring to up top, where they had a's, okay? A is a variable. If I let a equal 5, then in both pieces a is equal to 5. Okay, so the bases in this question are not the same, and therefore they are not equal. The other rule that we looked at, and that was, it's called the quotient rule, and that was for question 3 and 4, is if I have a to the power of m divided by a to the power of n, notice my bases are the same, then I can simplify this very, very easily by saying that this is a to the power of m minus n. So let's look at another example here just on the side. For example, if I had a was, I don't know, let's go with 7. Okay, so 7 to the power of, let's do 150 again. And below would be 7 to the power of 100. Okay, I don't want to write this in expanded version. It's going to be a lot of work, it's going to take up a lot of paper, and it's going to be a waste of my time. I can very easily say that this is 150 minus 100, which is just 7 to the power of 50. So my question for you is, can I use the exponent rule, or sorry, the quotient rule, for the following? Why or why not? I have 2 to the power of 5 divided by 2 to the power of 2. My answer is no. And it's for the same reason of the other one. The bases are not equal. Okay, so I have two bases, 2 and 5, and they are not equal, and therefore I cannot use the quotient rule. I think we all agree that 2 does not equal 5. Alright, let's do a few examples. So if I used my expanded method, okay, then I would write this as 5 multiplied by 5 multiplied by 5 multiplied by 5. I've got 4 of them. 5, 6, 7, 8. So this is all of my numerator. And my denominator is 5 multiplied by 5 multiplied by 5. Okay, I'm going to simplify some things. 5 divided by 5 is 1. 5 divided by 5 is 1. 5 divided by 5 is 1. And so what I'm left with here is all of this. Scroll my screen over a little bit. Hopefully I can fit it in there. I've got 5 multiplied by 5 multiplied by 5 multiplied by 5 multiplied by 5. And if I write this in index notation, 5 to the 5th. Okay, that was a lot of writing. If I use my shortcut, okay, 5 to the power of 8. Now, this is division. Okay, so we are taking the numerator's exponent and we're subtracting the denominator's exponent, and I get 5 to the power of 5. Notice that in both cases, as we should get the same answer, we do. One way, the shortcut, much simpler, much less writing, and it'll make your test go quicker as well. Alright, number 2. So let's write this in expanded version. So I could do expanded version. So a lot of writing here. So we've got 2, maybe we'll do a highlight there. Okay, so yellow, 2 multiplied by 2 multiplied by 2 multiplied by 2. So that was my first one, 2 to the power of 4. My second one, let's go with green. Got 3 of them. 1, 2, 3. And finally, the last one, oh man, there's 6 of them. 1, 2, 3, 4, 5, and 6. Okay, and then if I count them up, I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So I can write this as 2 to the power of 13. Now, if I had just used my shortcut, then I could have said, well, I'll write shortcut here. I've got 2 to the power of 4. Now, all of the bases are the same. This is really important. And then I can add the 3. Okay, so from the exponent there. It's a little hard to see now. And then I've got the exponent 6 there, so I'm going to add 6 as well. And I get 4 plus 3 is 7, plus 6 is 13, 2 to the power of 13. As expected, I get the same answer in both cases, but my shortcut, way less work. Alright, let's do number 3. So if I write this out in the expanded version, then I get on the top in my numerator, I've got 4 multiplied by 4 multiplied by 4, 3 times. And then I have 4 multiplied by 4, 4 squared. And my denominator is 4. I'm going to simplify this. 4 divided by 4 is 1, so I have 4 multiplied by 4 multiplied by 4 multiplied by 4 left over. And of course, if I write this in index notation, I have 4 to the power of 4. My shortcut would have been really nice. Let's see that. Okay, so on the top, they've all got the same base, and therefore the top is 4 plus 2. Okay, so I'm taking these ones here. And then, really, 4 can be written in index form as a 1. And therefore, I'm subtracting 1, because it's in the denominator. And therefore, I get 4 to the power of, it's 3 plus 2, which is 5 minus 1, 4 to the power of 4. So again, get the same thing. Alright, the last one. Now, I'm going to write this one out too, expanded versus shortcut. We're going to see a little trick here too. So we've got 4 multiplied by 4 multiplied by 4 on the bottom. Sorry, on the top. And then I have multiplied by 4 multiplied by 4. On the bottom, I have 7 of them. So 1, 2, 3, 4, 5, 6, 7. Okay, so I'm going to simplify. 4 divided by 4 is 1. 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 And finally, 4 divided by 4 is 1. Now remember, each of these, it's 1, right? So a lot of us make mistakes with this. What is the number on the top? What is in the numerator? If you just said 0, no. It's going to be 1. And on the bottom, we have 4 multiplied by 4. Which in index notation can be written as 4 squared. Alternatively, and we haven't looked at negatives yet, but this can also be written as 4 to the negative 2. And the reason I want to say this is because when we look at it using our shortcut, we're going to get 4 to the negative 2. And all it's saying is that the negative is telling us that it's 1 divided by 4 squared. So if you're a little foggy on that one, it's okay. I just want to make sure that we see when we use the shortcut. So we have 4, the top has a cube, plus it has a square, and then I'm subtracting 7 because the 7 is in the denominator, and therefore I get 4 to the negative 2. And these are the same thing, okay? And that is all for our first exponent lesson, exponent law lesson.